This is the first video on differentiability at a point. In order for f of x to be differentiable at x equals c, 1, f of x must be continuous at c, and the left-hand and right-hand derivatives must also be equal. If either one of these criteria fail, then the function is not differentiable at c. So, how does this look graphically? All right. A derivative can fail to exist at a point on the graph if at that point the graph either has a corner, that's this right here, a cusp, a vertical tangent, or a point of discontinuity. When you look at the first three graphs, 1, 2, 3, at the point that we're analyzing, so here it's 2, here it's -1, here it's 0, the function is continuous because there are no holes or asymptotes in the graph. So for graphs 1, 2, and 3, each of these functions is continuous. Why? Because there are no holes or asymptotes. But on graph 1, we have a corner at 2. On graph 2, we have a cusp at -1. On graph 3, we have a vertical tangent at x equals 0. So for all three of these, criteria 1 is true. It's continuous at the point we're talking about, but at the corner, the cusp, and where we have the vertical tangent, the left-hand and right-hand derivatives are not equal to each other. We'll see what that looks like in the first example. Now, for the point of discontinuity, for graph 4, we can see at 1 our graph is discontinuous, so it's not differentiable there. So you have 4 ways that this could look graphically. Now, we're going to focus specifically on these two criteria, differentiability at a point. Now, so determine if f of x is continuous or discontinuous, differentiable or non-differentiable at the value where the function rule changes. All right, so based off those two ideas, first thing I'm going to do is I'm going to look at continuous or discontinuous first. Because if it's going to be continuous or discontinuous, we got to check that first before if we check if it's differentiable or non-differentiable. To check continuity, you check the left-hand and right-hand limits. So I'm going to take the limit as x approaches 1 from the left of f of x. I'm going to use 5 halves x squared plus x plus 1/2. When I plug in 1, I have 5 halves times 1 squared plus 1 plus 1/2, which gives me 4. Now, the next thing I'm going to do is I'm going to check the right-hand limit, because for continuity, you check limits. All right, when I plug in 1, I have 2 times 1 squared, that's 2 times 1, plus 2, and that gives me 4. The left hand and right hand, that should be plus there. The left hand and right hand limits are equivalent, so yes, the function is continuous. All right, and we also see that if you plug in 1 here, f of 1 is defined. So we can put yes, continuous. All right, so we answered the first part of the question. We checked the left hand and right hand limits. Now, for part 2, so we looked right here. That was criteria 1. We checked the continuity. Second, for a function to be differentiable, you have to check the left hand and right hand derivatives. So before I start there, first thing I have to do is take the derivative. All right, so f prime of x will equal, all right, bring the power down, 5/2 times 2 is 5x. The derivative of x is 1, and the derivative of 1/2 is 0, so I just get 5x plus 1. The derivative of 2x squared is 4x. The derivative of 2x is 2. So now, when x is less than or equal to 1, and x is greater than 1. So now that I have the derivatives, what I'm going to do is check the left hand and right hand derivatives. So first I'll use 5x plus 1. Plug in 1 and you get 6. Now I'm going to check the right hand derivative. I also get 6. So now our left hand derivative equals the right hand derivative. So the function is differentiable. You could say, yes, it's differentiable. All right, so let's connect this back to what we talked about before. All right, so for a function to be differentiable, you have to check the continuity and the left hand and right hand derivative. That's what I did here. I checked the continuity with the limits, and then I checked the left hand and right hand derivative. So now what I'd like you to do is go ahead and pause the video. I want you to try this problem. Determine if f of x is continuous or discontinuous, differentiable or non-differentiable at the value where the function rule changes. All right, so go ahead and pause and try this. I'm going to keep going. So the first thing I'm going to do is focus only on the continuity. When you talk about continuity, you talk about limits. So I'm going to take the limit as x approaches 4 from the left of 1/2 x squared plus 5x. Plug in 4, I have 1/2 times 4 squared plus 5 times 4. That gives me 16 times 1/2, that's 8, plus 20, I get 28. Next, I'm going to take the limit as x approaches 4 from the right. I'll use the other rule, x squared plus x plus 8. Plug in 4, I have 4 squared plus 4 plus 8, and I still get 28. So the left hand and right hand limits are equivalent. So yes, the function is continuous. All right, now for differentiability. First thing that you need to do, all right, is take the derivative. So f prime of x equals, bring the 2 down, 2 times 1/2 is 1, so I just get x plus the derivative of 5x is 5. The derivative of 2x, or of x squared, is 2x. The derivative of x is 1. And I'll have x is less than or equal to 4. X is greater than 4. Alright, now let's find the left hand and right hand derivatives. Alright. When you plug in 4, you get 9. Let's find the right hand derivative. When you plug in 4, you still get 9. So the left hand and right hand derivatives are equivalent. So the function is differentiable. Alright. Now, so first we check the continuity, then we check the differentiability because of these two criteria. Alright, now let's do an application problem. Alright, where I don't see students making the connection is problems like this. So find the constants a and b such that f of x is differentiable everywhere. Now, it's the same idea as before, but now I'm finding constants. So, two things you have to check. You have to check the continuity and the differentiability. So, it's piecewise, so we got to check both of these criteria. So, let's start with the continuity. I'm going to take the limit as x approaches 3 from the left of ax squared plus b. You plug in 3 for x, and I get a times 3 squared plus b, which is 9a plus b. Next thing, I'm going to check the limit from the that's bx plus 4. Plug in 3, and I get 3b plus 4. Now, if the function is continuous, both limits must be equal. So 9a plus b has to equal 3b plus 4. Let's clean this up a little bit and get both a and b on the same side. Subtract 3b from both sides, and I get 9a minus 2b equals 4. Save this for later. Now, first thing, we check the continuity. Next, I'm going to check the differentiability. All right, first thing I need to do is actually take the derivative. So f prime of x. Now, a is a constant, so you bring the 2 to the front and multiply it with a. So I get 2a x. Now, b is a constant, so the derivative of b is 0. Now, in the second part of our piecewise function, the derivative of bx is just b. The derivative of 4 is 0. Now, the next thing I need to do is check the left hand and right-hand derivatives. So I'm going to start with 2ax. When I plug in 3 for x, I get 2 times a times 3. That's 6a. Now, the right-hand derivative, that's just b. You plug in 3, you just get b. Now, for differentiability, the left-hand and right-hand derivatives have to be equal, so b equals 6a. Now, I see I have two equations, two unknowns. I can create a system of equations. So I have 9a minus 2b equals 4, and b equals 6a. I'm just going to use substitution here, and I'm going to put the 6a in for b. So I have 9a minus 2 times 6a equals 4. That's 9a minus 12a equals 4. 3a, negative 3a equals 4. So when you divide, a is negative 4 over 3. Now, I still need to find b. I'm just going to plug it in back in. So I have b equals 6 times negative 4 over 3. That's negative 24 over 3, or negative 8. So this was the same concept as example 1, just we have variables we need to solve for. So now what I'd like you to do is go ahead and do this U-try real quick. The function f is defined on all real such that f of x equals x squared plus kx minus 3, for x is less than or equal to 1, and 3x plus b for x is greater than 1. For which of the following values of k and b will the function be both continuous and differentiable? So we're talking about continuity and differentiability, so it's the same concept. So go ahead and get started, pause the video, and then I'm going to start doing the problem now. So the first thing, check the continuity. All right, so I need to check the left hand and right hand limits. All right, so I'm going to take the limit as x approaches negative 1, or x approaches 1 from the left, of x squared plus kx minus 3, plug in 1, and I get 1 minus 3 is negative 2, so I get k minus 2. Same idea, just different variables. Now, let's go ahead and take the limit as x approaches 1 from the right. I'm going to use 3x plus b. Plug in 1. 3 times 1 plus b is b plus 3. Now, these must be equivalent if the function's continuous, so k minus 2 equals b plus 3. Let's clean it up and get all our variables on the same side. Add 2 to both sides, you get 5. Subtract b from both sides, you get k minus b. Now, next, and I'm going to save this for later. Now, I'm going to come over here, and I need to find the left hand and right hand derivatives. All right, so let's go ahead and first take the derivative. So f prime of x will equal, the derivative of x squared is 2x. The derivative of kx is k. The derivative of negative 3 is 0. The derivative of 3x is 3. The derivative of b is 0 because b is a constant. Next, let's check the left-hand and right-hand derivatives. All right, so right here, what I'm going to do is plug in 1. 2 times 1 plus k is 2 plus k. The right-hand derivative, you plug in 1, 2 times, the right-hand derivative, I'm messing up. So the right-hand derivative, I'm going to use 3. You can't plug anything in, so I just get 3. Set these equal. Now, I don't need to set up a system here because I can just solve for k. Subtract 3 from both sides. K is 1. Now, to be able to solve, I'm going to take this k equals 1, plug it back into my other equation. So I have k minus b equals 5. 1 minus b equals 5. Subtract 1, I get negative b equals 4. Divide by negative 1, b is negative 4. So k equals 1. When k equals 1 and b equals negative 4, this function is continuous and differentiable everywhere around its entire domain. So to review, differentiability at a point, you have to check the continuity and the left-hand and right-hand derivatives.